Buongiorno a tutti. Buongiorno, good morning to everybody. On behalf of the Italian Institute of Artificial Intelligence for Industry, I'm pleased to see you here for the third seminar of the Fondazione Compagnia di San Paolo Institute of Advanced Studies. A long name to say it's an Institute of Advanced Studies. It organizes classes and seminars and schools and so on for the benefit of the broader scientific and technical community in our institute, AI4I, in acronym, and for the local and international ecosystem. Indeed, you are here today, and for this I would like to special thank you for being here physically on a Monday morning, on the first day of academical year, under heavy rain with a strike in transportation. So thank you, I really appreciate this. Also a big thank to those who are connected, and please be aware that there are people online and that the seminar will be recorded and published on our YouTube channel. So welcome again. With no further ado, I would say today we are honored to host Professor Riccardo Zecchina. Riccardo is Professor of Theoretical Physics at Bocconi University in Milan, where he holds the Vodafone Chair in Machine Learning. Hope it's right. His research lies at the intersection of statistical physics, computer science, and of course, artificial intelligence. Join me in welcoming Riccardo, and thank you for being here.
So thank you for coming. As far as I can see, this could be a rather technical seminar, if you agree, unless you want a longer one. But so the plan was to have a general introduction about the state of the art in AI and some of the open problems that we face. And the second part is, should have been about some new solutions. So I think we can agree, unless you tell me the opposite, on kind of being very fast on the first part and focus more on the research results. So this would be a technical seminar and not a general introduction to state of the art in AI. Is that okay? Seems to me that you are all kind of experts in the field, so I don't think we should waste time. But in any case, since I have the slide, I'm going just to be fast in the first part and then go to the new results. Okay, so let me start with this engine, just to represent what's happening today in AI. So this was the first industrial revolution in the 18th century. The British built the first steam engine machines. And this is an example. It's called New Common Engine. It was built with thousands and thousands of exemplars. And it's kind of interesting because it's hard to imagine something less efficient than this machine. So I don't know if you see how it works, but here there is cold water which is injected in order to reduce the volume of the steam, but most of the energy is wasted in heating and cooling at each time the walls of the machine. So why am I saying this about AI? Because that was a period in which energy had almost zero cost for the British. Coal was very, very cheap, and so they just threw energy in a very, direct way without caring about efficiency. And notice that, so the efficiency of this machine was less than 1%, and the theoretical efficiency, if you do some thermodynamics, was about 25%. Several years later, the German and the French started to build machines. For them, the cost of energy was much higher, and then so they built much better machines, and even they developed the understanding of how the machine worked through thermodynamics. So somehow, AI is in a similar phase. Now we are throwing an enormous amount of energy, enormous amount of data into our devices, and so of course it's a different context, but somehow this is a good analogy. So this is what I wanted to talk about. So where do we stand in AI is in fact the first part, and I'll try to be fast. And then I would like to talk about how to implement physically learning on something that can in principle be built and not just simulated. And in this context, I would like to tell you about some new recent results that somehow are potentially changing the way we do certain type of AI. And in particular, I want to discuss the issue of how to perform learning without using huge gradients and doing all the simulations that we are doing nowadays with GPUs and cloud centers. Okay, so let me, well, this I can, very quickly. This is the story of machine learning in a nutshell. So essentially, everything changed in, well, I don't know if it doesn't. Anyhow, everything changed about 15 years ago when a group composed of Hinton and 2 Russian guys decided to insist in training neural network, and they were able to show that it was actually a very competitive tool for image processing and pattern recognition. So everything changed, and in particular, the amount of energy consumed changed enormously. So I'll show it to you here. This was somehow the amount of energy spent in research, let's say, on machine learning. You see, it followed the same curve for 60 years. Okay, it increased with a constant rate. All of a sudden, in 2010, the rate changed, and then changed again with the introduction of language model. And this is a logarithmic scale, so you have to imagine that this is an exponential growth. And what happens is that, essentially, if we would continue with this rate into the future, we would exploit all the energy of the planet in about 30 years. That's, of course, it's not going to happen, just for limitations. Another thing which is important to know, to remember, is that these are all the plots to 2020 about concerning the performance of language models as a function of the amount of resources injected, like compute time, size of the data set, size of the problem. As you can see, the test error, so the lower the value you observe, the better it is. And what was observed is that somehow these systems are bounded by what they call the universal law, or anyhow, this kind of curve. But, this has played an important role, not scientifically, nothing to be learned really. Also, the exponents are pretty small, so that's not particularly interesting in that perspective. But it was interesting because using this curve, it was possible to convince CEOs to invest an enormous amount of money, because the argument was, well, if you let me increase the size by a factor 10, I gain in performance, and so this has driven the investments in the US. Now. And so what we have observed is an increase in the size of AI. So now at the beginning we had few million parameters, this on the very bottom left, and then as following these curves in a sense, researchers and actually private researchers started to make bigger and bigger models, and nowadays we have systems that have more than 10 to the 12 connections. Okay, so this is an astronomical size, and this is why also it costs a lot of energy. Now, we don't really know how big is the latest version of GPT that is used, for instance, for ChatGPT. However, there's one thing which is important to notice, that somehow just the trick of increasing the size or increasing the data set is somehow saturated. This has been already several years ago. And so nowadays, the only way to keep the performance, say, increasing in AI is to inject computation it's called at test time. So I'm sure you have observed by using ChatGPT that if you ask a non-trivial question, the machine answers, well, I'm thinking. And it takes some time to answer. That is what is called compute at test time. And again, it has a big cost. And so the way now we are keeping performance, the community is keeping the performance of AI system increasing is by injecting compute, it's called compute, so a lot of computation, also at test time, and also it's a type of training which is done. And so this amounts also to injecting a lot of energy. There are some models, for instance, OpenAI models, that cannot be distributed just because, asking something to this model will have an enormous cost in terms of energy consumption. So you would not like to give to your kids ChatGPT with this option, such that you ask a query and then you have a $3,000 bill coming up just as a result of that. Okay, nowadays, again, just to be very fast, what is happening is that, as I was saying, this computed test time is changing the way the language model answer to queries. They perform what is called chain of thoughts. Essentially, you train the system to give answers in a structured way, so it's becoming, it's a little step towards AGI, and so there's been a lot of improvement in reasoning, in abstraction, in mathematical problems, and so on. Okay, I'm sorry if I'm sure you know all these kind of things. There have been two main players in the field. One is our LLM and transformers, the other are diffusion models. The first are generative models for AI, and I'll spend a few slides, very quick slides on that. And then there are diffusion models, which are a way of generating images from noise, of course, after a huge training process has been implemented. So there are two secrets that I would like to mention about generative AI. One is self-supervised learning, and the other is embedding, in the sense that the reason why of the success of generative AI is not just because the system were bigger, it's that because the way we train the system has changed. And the main trick, there are two main tricks. One is self-supervised learning, which allows the system to be trained on all the data available without any supervision by humans, this is a key aspect because we were, usually in the first phase of modern AI, like in deep learning, it was necessary to have data that were pre-processed by human in order to train this system. But then, using self-supervised learning, it was possible to start training the system without any human supervision, so essentially by using all the data. The data that could be used in deep learning for image processing, for instance, was just a tiny, tiny percentage of what can be used, in fact, for training LLMs or other systems. And the other is embeddings, the fact that the system represents words, tokens, images in a high-dimensional space, and this allows you to do very interesting operation. Now, sorry, I'm being very quick because I want to go to the technical part. So how does AI read a book? Just for those of you who are not familiar with this. So AI reads a book. We say ChatGPT has read all the text available, but what does it mean to read the text? It means the following, that you take a random sentence, in this case in Italian, and what happens is that some words get masked, and the task of the machine is to guess what it has been masked. So this is totally automatic, doesn't need any supervision. So for instance, this word here, it becomes the target of learning. And so you can do this for all the sentences, for all the text, for all the codes you have in order to train your system. So imagine you have to read a book in which you have, for all the sentences of your book, you mask the words and you have to memorize how to fill the gaps. I mean, for us, it would be totally impossible. So it's a totally different, non-human way of learning. But this is it, and it works perfectly well. Here maybe, oh yes, you can see it. I mean, GPT-3, these are all data, was already trained on the equivalent of 100 million books, 300 pages each. So by far more than what a human can even imagine to read. Another thing is our embedding. So the way the internal representation of the data that this machine have is based on a mapping in which words, for instance, in the case of languages, are projected in a very high-dimensional space, for instance, at 13,000 dimensions or so. And the way this projection is performed is learned. So the idea basically, and I'm sorry, I'm sure you know about it, but the idea is basically that you take this embedding, and then each token is represented by a vector in a huge dimensional space, and this vector can have an orientation, a length that depends on the context through what is called the attention mechanism. And so different words correspond to different vectors, but what it is important is that now you can perform mathematical operation on these vectors. So embedding plus the transformer architecture allow you to play with these vectors and give them a meaning that depends on context, and also in some sense you learn how to add and subtract words in a sense. You can do mathematics, a little bit of mathematics. And this is how then, now in the case of language models, you have an autoregressive system, namely the system learns to predict the next word, and in this way it can generate, instead of just guessing what is missing in a sentence, you train it to predict the next word. And this allows you to proceed and generate text given an input, a prompt. So are there alternative models? Well, this is less discussed and less known. Yes, there are alternative models which are inspired by the way we learn. For instance, this is a slide that I brought from Jan LeCun. It's the way, genetically speaking, the way we learn, human learn, is by comparing some prediction that we make on the external world with observations. And which means that we have to have an internal representation of the external world, rather than just eating up terabytes of data. So we need the capability of making simulations and make prediction about the external world. And this is a famous slide in which it is highlighted the fact that a baby learns the model of gravity when it's about 8, 9 months old. So that's the moment in which it develops a model of the external world in which objects are supposed to fall down. And if you show to the baby a flying toy when he's just 6 or 7 months, for him it's totally normal. But if you show it to him when he's 10 months old, then he's going to complain about it. Okay? So this is the way, it's not a solution, but the general idea. So it's a bit, and it is certainly different with respect to the way language models are trained. And these are called, so there's a whole, say, line of thought which is called world models. And essentially in world models, what happens is that the external information is projected and compressed into some internal representation of the machine, and then in this latent space, the machine becomes capable of, it's trained to make simulation, let's say, in the internal space, and then to connect the result of this internal simulation to the external, say, behavior. Okay, let me go ahead on this because I really want to keep it short. Okay, this is a movie obtained by this kind of simulation, okay, so you see this. Now, what is, in a nutshell, so let me go towards the content of the talk. What is AI today in terms of learning? What is deep learning in a nutshell? Well, deep learning is about having a huge system that depends on an astronomical number of parameters, and then in defining what is called a loss function. A loss function is a measure of how many mistakes you make on the data that are available for learning. Okay, so that's what is called a loss function. Deep learning is about trying to minimize this function. So you have a function, L, which, let's say, measures how many errors it makes, and so you want to minimize this. So you want to find the W's, the parameters in the network, in this case, the weights of the connections, that minimize the number of errors. Now, as you know, these are highly nonlinear devices that implement highly nonlinear input-output functions. So this function is actually highly non-convex. So in principle, gradient backpropagation, so gradient descent on this surface is not supposed to work. So gradient backpropagation was developed originally as a first-order method to solve convex problems, which you just have one minimum without troubles. In fact, this is, it turns out that it can be used for deep learning in non-convex devices. for many reasons, but let me go to the point. The main reason is not that there's something magic in backpropagation, in gradient descent, is that the landscape is not that complex. So the landscape has, has a structure with minima that are accessible. That's the main result that, it's not a theorem yet because it's very, very complicated, but this is the observation. This explains why gradient descent work. But let me make the point that if gradient backpropagation works, then gradient descent works, then there's no reason why other algorithms should not work, because the reason why it works is the simplicity, in a sense, of the landscape. So a priori, there should be other methods working. And this is actually, so do we need other models for machine learning? Well, one point that I'd like to make is that modern AI is an intrinsically software strategy. You do a lot of simple, huge mathematical operation, but you cannot build a device that learns according to this gradient descent. Why? Because each weight receives a signal that is, let's say, proportional to the derivative of the loss function with respect to itself, and it's something that should be, say, delivered to all the connection in the network. So it's something that cannot be implemented. It can be computed, but you cannot have a wire that sends this information to each node. So it's an intrinsically mathematical model, not physical in this sense. They consume a lot of energy for two reasons. Why? One is because of this kind of huge operation that need to be performed, like matrix multiplication, huge system, and so on, and also because they learn a lot of stuff. I mean, we do not learn the same way language models learn. We are not using an enormous amount of text in order to learn. We learn through fewer examples. So there are good reasons why this system consumes a lot of energy, because they're trained on an enormous amount of data, but there's also waste of energy. Now, there's a debate going on about the future, how this system can evolve toward AGI, and this is, it's difficult to actually comment about this because for many reasons. One is that we don't know exactly what's going on in private company research. So that's a problem. One thing that is clear is that this system do not exploit the dynamics of the network. So we know very well that our brain is a dynamical system, and this system have no dynamics at all. It's all just have a forward pass, and that's it, essentially. So it's kind of interesting, and it's a hot topic of research to understand how one can use the dynamics of, let's say, of artificial neuron, in order to perform learning. Okay, this is important for neuromorphic engineering, say at low power. It's important for learning theories, because you have to think a totally different way of performing learning, much closer to some biological reality, hopefully. I love this movie because this is a zebrafish in which you can see the neurons active. So when you see light, it's because a neuron is spiking. It's actually calcium concentration, but it's somehow related to the spike trains. And you see that essentially all what we have learned in AI doesn't tell us anything about what's happening in this little brain. Okay, and so maybe this is a kind of problem. So essentially the question, now I come to the new results, let's say. So the question I want to address is, how can a physical system perform complex learning tasks avoiding the propagation of these huge gradients? So just in a local distributed way, something that can be built. There's been a lot of works in the last years in this field, like we have well, I've divided them in three groups. One are techniques that try to approximate through a local computation, the gradient computation. So it's a way of mimicking what happens in deep learning through local computation. And I will discuss a little bit equilibrium propagation as an example. Then there are other techniques that do not try to approximate the gradient, are intrinsically different. In particular, predictive coding is quite popular in neuroscience. And then there are some kind of biologically motivated models like reservoir computing, which is based on the chaotic behavior of the network, and in particular, spiky neural network, which are built everywhere around the world, but they are not really successful because learning is highly inefficient at the moment. So nobody really knows how to train this system efficiently. So reservoir computing, for instance, is something like this. You have an input, you have a recurrent module, this one, and an output. This has a chaotic behavior. These weights are trained. And essentially, one uses this kind of system to do some signal processing. Okay, so you kind of exploit the rich dynamics of this recurrent network in order to perform signal processing operation. But for learning and classification, it's not very important. In predictive coding, sorry, I'm not going to tell you the details, but just the main, I highlight the main ingredients. For predictive coding, for instance, one needs two types of neurons, the traditional neurons that transmit the information, and some other neurons that are so-called error units that send back the information on how bad is the prediction of this neuron concerning the behavior of the neuron in the next layers. So, I mean, these are techniques that are very popular, etc. Now, I'm going to focus on a different model. But before doing this, let me tell you about equilibrium propagation. This is a technique that is developed by Chelier and Benjo. Chelier was a PhD student. And just a few years ago. But in fact, if one looks carefully at this equilibrium propagation, it's nothing but the Hopfield model, so for which the Nobel Prize was given 2024. So it goes back 1982. So this is a problem of current AI, that if you are a researcher and you're young, you don't know anything of what happened before, because there's such a flood of papers that it's very, very difficult to, in particular for students to have a handle on what's really happening. So what is this model? Essentially, this model is a neural network, recurrent, fully connected. So all the neurons interact with all the other neurons, so it's not a feed-forward network. It has its own intrinsic dynamics. But the key point is that these interactions are symmetric. The weights are symmetric. So if neuron I is connected to neuron J with a certain strength, neuron J is connected to neuron I with the same strength. And thanks to this, one can define what is called the Lyapunov function of the dynamics, meaning that this function in particular will be a decreasing function of the dynamics. So this system, by construction, is going to reach a local minima that corresponds to the fixed point of the dynamics of this system. Okay? So this is the Lyapunov function of an evolution dynamics that follows a simple differential equation or in discrete time. Okay, so you have this. These are just the update equation for the neurons. Let me not discuss the details here because I want to discuss it in another context, which is slightly simpler. But the idea is that you have equations that describe the evolution of the system, and thanks to the symmetry, you have this function that is going to, one can provably show that it's going to decrease with the dynamics, which means that essentially the system is going to converge and is going to end up in minima of this function. And so the way this system is trained is by dividing neuron in some input neurons, some hidden neurons, some output neurons, and then one forces the input neuron to be in a certain state. One, let's say, associate to the output neuron some cost function that measure how good is the prediction on some data that one wants to mimic. And then the system evolves and it reaches the fixed point. In one case, without the signal, the desired output, in the other case with the desired output, and based on the difference between the behavior of the neuron in these two cases, one can modify the weights in a way that is going to preserve symmetry and try to minimize the difference between the output and the desired output. That's the idea. And the signal which is injected is a small signal, because the idea is that one wants to just mimic the gradient. So the idea is to have a small perturbation such that the different states that are reached by the network can be thought of as a perturbation. And so it's actually a way of implementing a gradient descent. But the point I want to make is that it's really a system that is based on local minima, and that learning is something like trying to move this minima close to some ideal minima that one wants to build in the network. Okay? there are many limitations of this approach. One, the main limitation is that it doesn't appear to scale up. So if you want to use this strategy to train a transformer, I think you cannot do it. For instance, it cannot be used to do highly sophisticated tasks, like say ImageNet or things like this. So if you really try to use this system in a context of with benchmarks that come from AI, this seems not to be that efficient. Personally, well, in my opinion, one of the main limitations of this system is the lack of connectivity in the latent space. So these hidden neurons converge to fixed points, but there are many different such fixed points. And so as you perturb the system from the input, you're going from one fixed point to another fixed point, which are not necessarily connected. And this is not good for learning, because you want to cluster the internal representation and put together nearby inputs, right? Stimuli. And so that's the main thing. I think that's the main limitation that this system have. So we are paying a price for symmetry. Yes, we are going to have this minima, but these minima are not the ideal thing for learning. Now, the approach that I want to discuss is the following. First of all, I don't want to make any assumption on the couplings. I want to have generic asymmetric couplings, meaning that just like in the brain, neuron I connects to neuron J, and this doesn't imply that neuron J connects to neuron I with the same strength. No, we just take an arbitrary network. I want to use non-perturbative signals. I don't want to perturb them a little bit during learning, because what I want to do is to have something which is very robust. I'm not trying to mimic any gradient, okay? And I will show that one can design systems that are very simple, that given this type of assumption are actually performing learning very efficiently. Okay, and this is just been published. Now, let me take the simplest possible model. So let's take an asymmetric neural network, just a neural network like for equilibrium propagation or for reservoir computing. So the nodes here are neurons, nonlinear devices, and they are connected according to the arrows. Let's take a random, so let's take bistable neurons, plus or minus 1, just for simplicity. It can be done for continuous one. And then we assume that the connections are independent, so it's generically asymmetric. So we assume that the joint probability distribution of ijji is factorized. So this neuron, is going to interact with this one, but this doesn't necessarily going to interact with the other one. Now, and the system doesn't have any Lyapunov function. There's no energy for this system. The way we characterize the system is by defining the evolution equations. And here you see that each neuron, S is the variable of the neuron, at time t plus 1 is given by the sign of the signal that arrive at time t. So this is a nonlinear function of the input signal, which is the weighted sum of all the inputs coming from the other neurons. And these are the equations that define the model. And what is very well known for this system is, these are very old results, is that it is chaotic. So if you take it like this, it is totally chaotic. This goes back to 1988. Again, it's around the same period of field model. And then what do you do with this chaotic system? Well, you can do, again, some signal process, but not much more as far as I understand. So this is the kind of, at least to me, it looked like a desperate situation in which you, as soon as you make the system a little bit more realistic, it doesn't work. Okay. So I'm going I'm not commenting on the other, on this other paper just for the sake of brevity. So now, the way we modify this model, and it's not just a little trick. It comes from, say, years of modeling and studies. But at the end, in this context, the result is pretty simple. What we are going to do now is just to modify a little bit the model, and we just put a feedback, a local feedback, a self-interaction. So you see that the neuron at time t plus 1 takes a state which is given by the sign function of the incoming signal plus something which is proportional to the state of the same neuron at time t. So if you just forget about the signal coming from the other neurons, this describes the evolution of, say, a bistable system in which essentially all the states are fixed points, because if this is absent and if this term here is positive, this equation is always satisfied for any possible state. Okay, so we have a system in which if this J is large, it's going to have a lot of fixed points, and if J is 0, it's going to be totally chaotic. So it's kind of a way of actually start to understand what happens. Again, the choice of this way of simplifying the system is just for simplicity. There are other ways that I will mention in a minute. So we take the same model as before with asymmetric coupling with just this little modification. And first of all, one can compute how many fixed points you have. This can be done rigorously. It's just a first order, first moment calculation, which is exact. Namely, that if the self-coupling is 0, you have this 0 fixed points. This is 1 over the log of the number of fixed points, because it's an exponential number. And if you take J large, this curve converges to log 2, which means that all configurations are fixed points. So far, so good. Let's say we are starting to inject some reasonable behavior in this system. But a closer look, using techniques from theoretical physics, shows that these fixed points in the phase space are totally isolated. So you don't have a cluster, say, or a basing of attraction, say, around a fixed point, something like this. These are just like a golf course. You have a lot of fixed points, but there's always a big Hamming distance between different fixed points. And this is bad news, because given there's a theorem, which is called the overlap gap theorem, which tells you the following, that if you have isolated minima of an combinatorial optimization problem, in this case, these are just the fixed points you are looking for, because you can always think about finding the fixed points as minimizing this function that counts how many neurons are not aligned with the incoming signal, right? So you can always turn the search for fixed points into an optimization problem. Now, what happens is that due to this theorem, there's no way a stable algorithm, which includes gradient descent, any kind of dynamics, can actually reach this isolated fixed point in a polynomially bounded time. So there's a theorem that says, OK, you might have a lot of fixed points, but given that this is the shape, this is the geometrical structure of the fixed point, you are lost. OK? Good. So, but then if one runs simulation, one finds that it's true that for J small, it's impossible to find this fixed point. But if J is sufficiently big, algorithms start to work efficiently. So what's going on? On the other hand, on the one hand, you have a theorem telling you, no, there's no way. On the other hand, you do find them. So the way out of this is that, in fact, in this sea of fixed points, there exist rare regions of fixed points that compose clusters that are highly connected, that are close by. So the theorem is violated, the hypotheses are violated, and so it doesn't hold anymore. And in fact, algorithms do work. So, and why didn't we mention this connected region? Because when we do the calculation of a number of fixed points, since this is an exponential number, the isolated ones are those that dominate the computation. These are rare events, are second order effects. Okay, this is a mathematical aspect, doesn't matter, that's just missed by the calculations. Okay, but now if you look at this problem from the point of view of an algorithm, you actually essentially don't care at all about these isolated fixed points, or minima. You just don't see them. There's no way of actually addressing them. So what is interesting for you are actually the onset of these connected solutions. Okay, some years ago we developed a mathematical technique which is based on large deviations to search for these regions in mathematical problems. And the idea is essentially to explore the space of minima or of fixed points. Instead of looking for points, single points, you explore this region by considering a hypersphere. and optimize in the center of hypersphere, and the cost function we want to optimize is the number of fixed points contained in this hypersphere. That's the idea. So instead of looking, it's like saying you have a golf course. Instead of looking for holes, you look for lakes, little lakes. That's and this is, and these lakes can be very rare compared to the holes in the golf course, but this is what is needed to understand what happens. Okay, so let me make this story a bit relatively short, in the sense that one can implement, it's called the local entropy approach. So essentially local means you look for a region in the space of configuration of your network, and you try to optimize what is called the local entropy, namely the number of fixed points contained in a certain region by optimizing the center. So it's a mathematical technique, but this will have algorithmic consequences. So if you do this, essentially you develop a method that allows you to identify, when you have a very rugged landscape, minima that are like this, as opposed to minima that are very narrow, but can be exponentially more numerous. Okay? So that's the thing. And okay, so by doing this, let me skip, we can actually apply it to our problem. And what we find is something like this. Here you have the distance from the size of this hypersphere. So the distance from the center of the hypersphere that we have optimized in order to see if there are these dense regions. And here is the number of fixed points contained in this hypersphere. So you see that if the self-coupling is small, you have that this internal log of the number of fixed points is negative, which means that there are no fixed points, essentially. So if j is less than, say, 0.01, or if it is 0, you have just no fixed points at short distance. This distance is pretty small, but if you are at short, which means that around these isolated fixed points, you have nothing. Okay, so nothing happens. At a certain point, if you increase the self-coupling, you see that this is the 0 value, the internal entropy becomes positive, and which means that you start to observe something around, you start to observe the existence of lakes that are dense in number of fixed points and close by. And if you still increase j, all of a sudden these lakes become extremely wide. You see, well, it's a bit difficult to, anyhow, what happens is that if for intermediate values of j, you have little lakes, let's say, still isolated, but not point-like. And then if you increase j, this lake fuse together and they become huge regions of connected solutions. So let me, maybe I can show it here. So if the self-coupling is small, you just have either isolated fixed points or little clusters of fixed points. And these are not accessible by algorithm because of the overlap gap property. At least we have not proven this, but it's likely to be so, that also these little clusters are isolated from the rest, so they are not accessible by stable algorithms. But beyond a certain value of the self-coupling, all of a sudden, this little cluster becomes connected, because as you increase j, the fixed point constraint become weaker and weaker, so this region becomes connected, and you generate a huge region of connected fixed point that we call the representation manifold. These are the internal states, stable states of the network that are accessible by algorithms. Okay? So this is the first key result that was not known in the literature. So if you take asymmetric neural networks and you just simplify them a little bit, then what happens is you add a few ingredients like a self-coupling or some other ways of inducing this that I will discuss in a minute. You may have the onset of this internal representation manifold that are stable and accessible by algorithm. And therefore, you can implement learning, and you can use them for learning without any assumption on symmetry, energy, whatever. Okay? This approach can be extended to multi-layer networks. In particular, we can consider modules that are of the type I've just discussed. So each module is a recurrent asymmetric network with some self-couplings. But then you can couple different modules through a positive interaction. So let's say that neuron number 1 in this module here is connected with a positive coupling to neuron number 1 in the second layer, and so on. So you can actually develop a model which is a multi-layer network. And this differs from the standard multi-layer network used in deep learning or in language models because these are recurrent modules. So they need some time to settle down. They have an internal dynamics. But the key point I want to make is that, let me say it in words, is that if you build a deep network like this, then you can actually set the self-coupling to 0 and just have this coupling between modules, and this will induce the onset of this representation manifold, so it becomes stable. So by connecting different modules, they actually become stable and accessible by algorithms. So if you cut this connection, they are chaotic. As soon as you connect them, they become, let's say they synchronize somehow, and they become stable. That's the main idea. So I'm going to skip the analytical calculation, but one can show that, just by computing the number of fixed points, you see that the self-interaction and the coupling play a very similar role. Mathematically, one can show this. And yes, these are the kind of curves we find for the internal entropy of these hyperspheres. So what I'm saying is that if the coupling between different systems is 0, then you have the same behavior I discussed before. If J is very small, you have a negative entropy, so no solution at short distance. And then if J is sufficiently large, you have an exponential number of solutions over long distances. But the same behavior happens even if you actually set the self-coupling to 0 and you increase the coupling between modules. Okay? And this is something which was not known. And then we use this to define what we call the representation manifold of the external world, meaning that if you now inject some signal in this system through that comes from the outside, inside, so each neuron receives the signal from the other neurons, say the self-couplings. This is for just one module. Plus, it also receives a signal from the external world, and you let it converge. Then the system converges to some state, let me call it eta, which is nothing but the internal representation of the external signal. And these etas compose this very heterogeneous connected structure in the representation manifold. Okay? So one can run some numerics on this and show that, in fact, if you find two fixed points and you try to connect them through some intermediate signal that map one fixed point onto the other. I mean, suppose you have, say, a fixed point, an external signal psi1, which is one image of a cat, and psi2 is a dog, and you want to know what happens in between. Let's say this would be the idea. So you can stimulate your system with an external signal, which is a mixture of the two. And you look at where it converges, then you observe that there are a lot of very interesting paths. First of all, you observe that the manifold is connected, and that it has a kind of a hierarchical structure. Okay, these are, depending on how you do it, you can exploit different characteristics of the geometry. But this is the geometry of this hidden, of this internal representation. Okay, so how to implement learning so that I can go to the point? Well, the idea is the following. Suppose that now you have, these are the equations for a multi-layer system. So you see that now neurons also have an index L, which corresponds to the layer. And the idea is that this system evolves. And as I mentioned to you, it's going to converge only if either lambda or j is sufficiently big. So let's consider the case in which j is 0, let's say. It's kind of interesting to observe that if we do not have, we are not connecting the different modules, all the units will be chaotic, right? But as soon as you put some interaction, what happens is that they convert to a state, and this means that, say, the neuron here is correlated to a neuron there. Everything becomes correlated on a long scale, from input to output. And this is what we are going to exploit for learning. So let's do a very simple experiment. We have a multi-layer network. We force the first layer to be in the all +1 state. So we force through an external signal the neurons in the first layer to be all +1. Then we have many layers, and we force all the output neurons to be, say, in the state -1 or an arbitrary state. What one observes is that even without learning is that the dynamics of the intermediate modules, when lambda is sufficiently big, adapt and rotate in such a way to map the input to the output. Essentially, this is a device that very quickly can settle down into a dynamical state that can implement an arbitrary input-output function through the dynamics, which is really the prerequisite for learning. Okay? And then we can exploit this for learning purposes. And this is the last part I want to mention. So let's consider the simplest case, just for the sake of simplicity, in which we just have one module. We can do it for multi-layer, but let's do it for one module. And so we need, since it's one module, we'll need to have some self-coupling in order to have this stable manifold, this representation manifold. And learning goes as follows. You have some patterns, like, say, images and label of the image. Okay, let's think to MNIST that everybody knows. This is the picture of handwritten digit, and this is the actual digit, the label of the digit. Okay? So we have an input layer. Let's say here you have your image, and this input layer projects, gives a contribution to the incoming signal to each of the neurons in the module. Right? So you have a signal coming from the input, which is given by this term. So you have some W times X, which is the picture, the pixel of the picture, okay? So you have your neuron evolve according to the following equation. So S times T plus 1 is equal to some nonlinear function of the signal coming from all the other neurons, the self-coupling, and then here you have the signal from the input. But we also want this system to settle down to a configuration that outputs the desired label. So the idea is the following, that you also have an output layer. This output layer has some connection that go from the output to the recurrent unit and some other connection that go from the recurrent unit to the output. And you also want to force this output layer to be in a desired state. So the idea is that you force the input, you force the output, and you let the system settle down. So it's non-chaotic, so it's going to settle down. At that point, you can try to stabilize the system and implement learning, right? So the idea is that you let it converge. Once it has converged, what you just need to do is to reinforce the stability of all the neurons given the input, right? And if you can do this, you can actually learn. This is and this can be done on a neuron-by-neuron basis. You don't need a cost function. You just need each neuron to stabilize its own state. So its label, its desired state, is actually the state reached by the dynamics, and the input is given by all the other signals that are arriving. Okay? And so you can actually think to this network as a composition of many perceptrons, so elementary units, neurons, and what you want to do is to stabilize the state that has been reached by the dynamics. So there are two learning strategies. The first one is kind of simple to understand. So you have an input field and a desired output field. Let's say an image of a 1 and the label 1. And of course, for the label, we use a one-hot encoding of the output unit that you probably are familiar with. And so what you do is, given these inputs given these signals from the input and the output, so this supervision, you actually converge to a fixed point that we call S star. In few steps, actually, it's very quick, the convergence. At this point, you want to stabilize this state, but in such a way that you want to stabilize it in absence of the information from the output. Because when you're going to use this network, the only signal which is available is the input, not the output, right, at inference time. So you use the output to find the fixed point, and then you train it by deleting the contribution from the output. So you want to stabilize this internal representation without the contribution coming from the output. This is a key observation. And then you can do this just by using a simple perceptron rule. a local rule. But the key point is converge, delete the contribution from the output, stabilize. And this is possible because there exists this manifold. Otherwise, this would not be possible, right? So, and this rule is asymmetric, so it's not preserving any symmetry. A second way of doing it, which is quite surprising, at least to me, is the following: that you have, again, you use the same protocol at the beginning, so you have an input and an output signal, you converge. And once you have converged, you find this fixed point S star. At this point, after this first transient, you switch off the output and you converge to another state S star star, right? A second state. So at the beginning, you have both input and output. Then you converge, you delete the output, and you converge again. And you converge to the state S star star. And then you stabilize that state. Now, this is going to work because what happens, and then you stabilize again with a local rule. But the key point is that it turns out that due to the geometry of this manifold, S star and S star star are very similar, almost identical. So essentially, you don't need to, cherry pick. Oops, sorry. You see, in the previous approach, we had to converge, and then for each neuron, we had to go there and delete part of the signals coming from the other neuron. So somehow we had to supervise the system and just delete certain contribution. No, this is not necessary. You just need to switch off the output signal and let it converge. No cherry picking. And this is very biological or very electronic, depends on your interest, right? So, and if you do this, again, what happens is essentially that you converge to a point on the manifold, and then when you switch off the output signal, you just remain very close by. Actually, the difference between these 2 points is extremely small. They're very close one to the other. Because this is related to the high-dimensional nature of this manifold, to its branching structure, there are a lot of geometrical properties that enter in the game. But everything is for free. I mean, we have not designed this. It comes from essentially the randomness of the system. And one can show that in order to, so these are some tests. We have run this, let's say this model on not on MNIST directly, which is too easy, on a slightly more sophisticated version in which we take MNIST, we compress it to 100 dimensions, and then we binarize, so we perform a nonlinear operation. Why did we do this? Because in this setting, a linear classifier doesn't work. It has very poor performance. So we try to make MNIST just a little bit more difficult in such a way that, without some, say, deep learning, the learning would not be effective. So just a linear one, so no hidden layers would not work on this bench. I am perfectly aware that testing something through MNIST is a bit kind of almost 30 years old kind of strategy, but we didn't have time to do more than that. So, and one can see that the train accuracy and the test accuracy on this benchmark become effective, become high, only if JD is sufficiently large, so only if the manifold is present. That's and these are the data. Well, essentially, you should look at this. I mean, for a small network, what you have is, this is the performance of the network, the generalization error of the network that has been trained by this local procedure that exploits the dynamics of that exploits the internal representation manifold, and these are the performance of some other classifiers that do not do that. Again, I don't care about the numbers here. I just want to, the scope of this is just to show that there is an effect of using, a positive effect of using this internal representation, and it works. Some interesting things that have to do with energy is that, first of all, the training is extremely fast. Very few epochs are enough to converge. And the fraction of neurons that are actually involved in training, when you try to stabilize the fixed point, is extremely small. So this means that you have to adapt just very few neurons, and it's going to work and generalize well at very low energy. That's the another thing that is kind of interesting is the following, is that if you initialize your system with purely symmetric coupling, so the idea is, do we need this symmetry? Was it a good idea to give the Nobel Prize to Hopfield? No? Of course it was, but so you can initialize your system with totally symmetric couplings and so this is the degree of symmetry in some measure, how symmetric is the Jij matrix, the Wij matrix. And you start your system with a totally symmetric matrix. As learning goes on, it reaches this level of symmetry, which a fraction of neurons have symmetric coupling and another do not. And if you start your system with a totally totally asymmetric matrix, you reach more or less the same level. So it's totally wiped away. And in fact, one can show that if one implements a learning rule which preserves symmetry, one finds the following, is that if one considers a system in which the manifold is not present, so the JD or the lambda are not big enough, the performance are very poor. On the other hand, if the manifold is present, the performance are good, which means that essentially symmetry doesn't play any role. It's just the manifold that plays a role. Okay? So, okay, this is a little movie of what happens with the internal representation. So here, what we do is the following experiment. We give 10 examples for each digit in this MNIST, and we let it converge, and we look at what is the overlap of the internal representation. So how the ones are similar to each other, how, say, or the zeros are similar to each other, how they are different from the other. So we just compute the scalar product between this internal representation, and we built up this matrix. And if you do this, you obtain this evolution as learning goes on, and you see that it becomes more and more clustered, and this is actually useful for learning. Of course, you can immediately see that, let's say, these squares are creating trouble because what this is telling you that 3 and 5 have some similarity in the internal representation, which is not surprising. They look pretty similar, right? But okay, with this kind of internal representation, you can actually perform learning. Okay. So I think I can, it's more than an hour, so it's an hour and I think I should stop. So what I want to highlight is the following, that first of all, the existence of this connected manifold is what allows many algorithms to converge, the simple neural dynamics, but also other type of local algorithms to find these fixed points. And so this is the key ingredient, which was not known before, but that's not a particularly important thing. What is interesting is that it's extremely useful for learning because you can converge and then just stabilize through local rules. And we know how to induce the presence of this manifold by self-coupling, by coupling different systems. There are different strategies. In neuroscience, for instance, it's quite known that neural networks have some subnetwork of strongly positive excitatory neurons. Sorry, of excitatory neurons, which means that you should imagine your network with a lot of interacting neurons, and then on top, you have a sparse network with a lot of positive coupling. This is going to play essentially the same role. So whether this is biological or not, we'll see, but for sure, at least from the engineering point of view, this allows to implement system with a totally local update scheme, which works, and it's a very low energy kind of system. And then, of course, there are many things that need to be done, like, say, scale up the system to check what happens. This system can be implemented on a convolutional neural network, on a transformer. In principle, this can be done. And we are actually starting with a lot of students that are engaged in this. They are going to play with this model and try to see what happens. And also, we're going to collaborate with some neuroscientists in order to build models that just to see if this kind of behavior is what can be also relevant in biology, okay? So this is more or less the onset. So, for instance, in the case of engineering, one message could be the following. You know that a lot of so-called spiky neural networks have been built. There are a lot of startups doing it. But how to train them is a nightmare, because you have this spiking neurons, and you have to do backpropagation through time in order to control the behavior. At the end of the day, you don't find spiking neural network around. They are not used, okay? It's very difficult to control them. Even though they are very interesting, they consume very little power. Now, now we have a strategy, say, if we can induce in the spiking neural network this manifold of internal representation that are stable, then we can use just a very simple strategy to train them. So it's kind of nice and fun, I think. Okay, I'll stop here. If we want to have any question, I'm happy to answer. If not, we can drink something.
I can speak without the microphone.
It's just for the people online, I guess. Usare questo. Do you want to use this one?
As far as I know, in human brains, for example, the chaotic phase is really important for the learning. While here, if I understood it correctly,
you have to motivate that state.
okay. No, I'm not an expert in that, but I knew that the chaotic phase was the one retaining the most of the learning.
No, this is, sorry. I mean, the fact that some chaotic behavior is observed, for instance, if you have a seizure or something like that, it's clear. But how to use chaos for learning, I'm sorry, but it's not a statement that's scientifically solid. I mean, one argument which is often used is the edge of chaos. What does that mean? It means that if you want to be in a situation such that two inputs that are very close, they are mapped into similar states, and they're a little bit different. They are mapped, if they are different, they are mapped to different states, which means that your system is sensitive with respect to difference in the input. So being at the edge of chaos more or less kind of implements this. But if you can show me an example of a network that works based on, that performs learning based on chaotic behavior, I would be happy.
I have a couple of questions. One is more technical, one more broad, maybe. The technical one is, you first present the output.
Yes.
During training, so let dynamic converge, then you remove the output and you have the, starting from the previous final condition, then you let the system evolve to a new fixed point. What happens if you do the opposite? I mean, you first converge freely without the output constraint, and then you insert the output. Would that be different? Or?
It would be different for sure, and I wouldn't know how to use it, because you see, if you train your system in the presence of the output, then it's useless, because when you want to use it at inference, you cannot give the output. The output is something that you have to read, so you can only give the input. Yeah. So it's interesting from a geometrical point of view. It's interesting to ask the question, how is the shape of this manifold? And so you can do many experiments in which you might reverse the order and see what happens. It's totally legitimate from a geometrical point of view. But from the point of view of learning, if you train with the output, it doesn't help, right?
Second question, I mean, why do you expect, I mean, connected to the first part of your talk, why do you expect this kind of learning system to be more energy efficient?
Yeah, so of course, if you use this system just to train an LLM, thing that I would not do, because we wouldn't gain much. I mean, yeah, maybe, some fraction, I don't know. It remains to be seen. There are two considerations. First, this could be implemented in hardware. So you use GPUs because you want to simulate matrix products. You are not actually performing matrix products with the circuit. So modern AI is about software, it's not about hardware, let's say. Of course, you have hardware to accelerate the software, but it's not a direct map. But I personally think that this kind of model are of greater interest for world models. Why? Because you have the internal representation that really play the key role. For instance, you could have an input signal that represents a table with a bottle on top of it, right? And this is the input, an image. And then the system would convert to some internal state. At this point, in this internal state, you might have other inputs that represent actions. And you let the system evolve in this internal space, and at the end, you read out in the input space the effect. So it's a way of making simulation within an internal space. So this is just wishful thinking. We have not implemented this yet, but it could be done. It's a natural setup for that.
So you do training by dynamics, essentially. How long is this dynamics usually?
Of course, it depends on the data, but it's very short. I mean, say 5, 6 updates of the network is very rapid. Otherwise, it would be useless. Bene. So thank you very much for coming. Thank you.
Just a few things. I want to thank Professor Zecchina for being here with us and all of you to participate and the people that are connected through the webinar. Your feedback will be precious, so don't hesitate to let us know something about the seminar and the experience. And I want to recommend even that in a few days, the seminar will be uploaded on our YouTube channel. So the next appointment with IAS will be on October the 21st with Professor Marco Zanfalon, that is University Professor and Scientific Director at Dalla Molle Institute for Artificial Intelligence Studies in Lugano. He's going to talk about trusting generative AI, reality, dream, or nightmare, a deep dive into causal AI. So thank you very much for being here with us, and stay tuned for the next appointment.